Okay, so welcome back, and today we're going to start talking about another model. This is called the Logistic Growth Model. So where does this come from? Well, it comes from the fact that when we talk about exponential growth or exponential decay, especially with exponential growth, we talk about, like, say, bacteria in a petri dish, or we talk about rabbits or some animal within a certain habitat or geographic region. And so a lot of times mathematically, when we talk about exponential growth, we think that this has this exponential curve, but the exponential curve assumes certain things that are not really realistic, okay? For example, the exponential growth model assumes that you can grow to infinity, right? It doesn't take into consideration size of the habitat area, predators, the predator-prey, resources, food, water, things like that, right? So all of those things inhibit, at some point, the continuation of exponential growth. So that means, what am I saying? Well, in the real world, in nature, things don't grow exponentially forever, right? There's only so much resources before animals start starving, or things like that. Okay, so the logistic growth model takes this into consideration. And so, what does the logistic growth look like? Well, it looks like something like an S-curve. Okay, so here at the beginning, let's say we introduce an animal in a habitat. And what's happening, it's going to grow exponentially. It has like this exponential growth here up to a certain point, okay? And then what it's going to do is it's going to start to slow down. The growth rate is going to start to slow down and start to even out as it gets closer and closer to this line. And this line we call is the capacity, okay? The capacity of the environment. So this depends on resources like food and water, predators, right, and things of that nature, okay? And so it starts to flatten out, okay? And so this is what the logistic curve looks like. So this C value, this is the carrying capacity for the environment. It's a constant, right? This here, this initial amount is given by this point, so 0, comma, C divided by 1 over A, right? Because if X is 0, right? If X is 0, this becomes 1, and you get this point. Now, the point at which the growth rate starts to slow down. So here, the growth rate, right, is going up, okay? And then it starts to slow down. The point at which that starts to slow down is the inflection point of the curve, and that happens to be when the number of the population, if you will, the population gets to half the capacity. So when you reach the halfway point of the capacity, that's when the inflection point in the growth curve starts to decrease. Okay, and so if you want to know the value of X, which is the time, if you will, or the value of X that will happen, is going to be located at the natural log of A divided by B. Okay, so again, C is the carrying capacity, or what we call the limiting value of the environment, the habitat. B is the growth rate constant. So that's the growth rate constant based on the situation. So if we're talking about growth of petri, growth of bacteria, the rabbit population, squirrel population, wolves, deer, these all have certain constants, growth rate constants that we have to consider, okay? And that's the logistic model. And here's the function, right? So here's the model. So it's the carrying capacity divided by 1 plus A, which is the initial amount here, Okay, so A, in fact, do they give a specific... Okay, yeah. So A, I believe is the initial value, but I'll find out in a minute. Yeah, this is the curve. This is the function that gives this graph. And that's it. So now what we'll do is we'll do an example, and we'll put this to work and see how it works. See you next time.